Welcome. Today's physics experiment is going to be on spectroscopy. You can follow along in your lab manual. We're basically going to be doing the exact procedure in your lab manual for this online version of the lab. I'm going to actually do my notes from here as well because I don't want to have to draw all the pictures. So here we go. You're probably familiar with spectroscopy from some of your chemistry courses. But let's just review the basics here. If we were doing this in lab, we'd be using what is known as a diffraction grating, which is just a little piece of plastic that has a bunch of parallel slits that are spaced really closely together. And what happens when the light passes through those slits, there's a blow up here, there's the light, it's coming in parallel rays, right? Passes through these slits and it gets diffracted. This is not totally unlike refraction, which we studied before, in that the light gets bent, and it's bent differently depending on its wavelength, but it's a slightly different mechanism. So here the light comes through the slits, it's bent, and what you end up with is a spectrum, much like you would get from a prism and refraction. So I just want to take a minute to look more closely at this. We kind of zoom in here, and what we see are these parallel light coming in, but when it passes through this little slit, it doesn't go on the same path anymore. So if I look down here, we can look at this little triangle. Here it is, blown up, and this gives us a sense of how diffraction is going to be related to the wavelength or the color of light, which is why we can use diffraction to produce a spectrum of light. So here's the equation that I want y'all to look at today. And it says that D is this separation right here, separation between those slits in your diffraction grating, times the sine of the angle. Okay, and this angle here that I want to talk about today is actually the max angle. So this little m stands for max. It's the max angle here, right here at the top of this triangle. Okay, that is going to be equal to m, which is just going to be a number, a constant, times the wavelength of the light. So you have D separation times the sine of this maximum angle. M is what we're going to call the order. We'll get back to that in just a second. Times the wavelength of light. The reason that I write this equation, the importance of this is that this wavelength right here, the wavelength of light is directly proportional to this D and this angle. And the angle in particular is what I'm worried about, because we go back up here and scroll up a little bit, right? Notice how you can have light coming through these slits, but leaving here at different angles. If you have a different wavelength, you get a different angle. So, oops, sorry, my pen wants to do weird things there. So, light coming through here might have a different path depending on its wavelength. That's the main point that I want you to get out of this. That a diffraction grating separates light by its wavelength. So let me just write down here. The angle then is directly proportional. So the angle, directly, boy, I'm having trouble writing today, is directly proportional to the wavelength. Okay? Notice it's also inversely proportional. The angle, is inversely proportional to the slit. So this means as well that the slits matter in your diffraction grating. If we were in class, I could show you two different diffraction gratings with different slit separations, and you would notice you could see a spectrum easily out of one, but not out of another. So that's another little piece in there. But this is the main point, that the angle is directly proportional to the wavelength. All right, so your lab manual talks about that a little bit more. Now I want to get back to this idea of order. Okay, let's look at it first here before we switch to the next image. So order means that you get more than one spectrum when the light passes through. As you sort of have this direct path to the zero order, m equals 0, and then you have these bent paths to first order. Let's look at what that would look like if you go to the next page of your lab manual here. Let's focus in on the rainbow here for a minute. Here is our 0th order. We have light passing through that grating, and it goes through, and it's still white. It didn't get separated by wavelength. That's the 0th order, right? That equals 0 times the wavelength. Here, though, is where our spectrum is. And you notice now that the blue comes through at a different angle than the red, and you get the whole rainbow. So here again, we're reminding ourselves of that proportionality between the angle and the wavelength. But look, you can have more than one order. So first order here, second order here, that's that M. You can have for a larger M, remember the M was right in there, you have a different angle. So you have repeated the rainbow. Looks fainter, looks spread out. So as you get further away from that 0th order, that angle wavelength dependence is shown by these further orders. Okay, so that's the whole rainbow. But we're going to be focusing on lines today. So with a spectrum, you can have emission lines. Remember your chemistry, right? This is an emission spectrum where you have those little electrons inside of an atom. They're jumping energy levels, right? And when they go from a higher energy down to a lower energy, they emit a photon of light. And so that's what you see here. That photon of light, the color, is determined by the difference in energy levels. I'm not going to review all that chemistry. So here we have a blue line and a red line. Right? We have their different wavelengths. The wavelength determines the angle. How far are they away from each other here? And we can then use this emission spectrum, these emission lines, to identify what type of atom we are looking at, because some atoms will have very particular lines. Some, like hydrogen, only has a few. But as you go up the periodic table, something like oxygen would have many more emission lines. Okay. All right. Moving on here, you can read more in your lab manual. Let's actually look at a spectrum here. Here's hydrogen's emission spectrum. Remember, it's a very simple atom, so it only has a few bright emission lines. There's a few others hidden in here. We have some doublets, but you're just going to be seeing the bright ones. And I'll show you what that looks like when we get to talking about the procedure. One more little application. Here's helium. We're going to be looking at hydrogen and helium today. One more application, since I have your attention here, is you may have seen this in chemistry, like I said, but spectra are really, really useful in astronomy. So as an astronomer, you get the 5-minute version from me about spectroscopy in astronomy. So here are different spectra from different types of stars. So stars emit absorption spectrum. You're going to be looking at emission spectrum today, but absorption is the other way. right? That's when that electron wants to jump up an energy level, and so it takes in a photon, and you end up with dark lines absorbed out of the continuous rainbow of spectra. What these are useful for in astronomy is looking at the different colors of stars. This star right here puts out more blue. This one at the bottom puts out more red. That's great. Stars are different colors, but what else can we know? Well, this tells us about the star's temperature, because color and temperature are directly related. By looking at these different types of absorption lines, we can tell what is this star made of, its composition, which is really, really awesome. This is how we know what stars are made of. By the way, here is our sun right here. It is a G2 star. Look, it puts out all the colors of the rainbow. It has a peak here in the yellow and green. That's where it puts out most of its visible light. So that's our sun. So we can tell temperature, composition. The temperature is linked to the color of the star. These blue stars are the hottest, and the red stars down at the bottom are the coolest. We can also get information about these stars' velocity if they're moving. We can use Doppler shift to, with these spectra, to figure out cool stuff like that. But just wanted to give you a little bit of background on one way that we use spectra. Okay, so before we run out of time here, what are you going to be doing in this lab? You're not going to be making movies with real spectra, sorry. But you're going to start using this tracker software. You're going to have to download it to your computer, look up physics tracker on Google or whatever your search engine is, get your Windows or your Mac version, download it. Won't hurt your computer, it's perfectly fine. You'll download it and it'll look like this. Well, it won't look like this when you first open it. When you load in your movies, you'll get your movies off of Moodle. There'll be two different gases, and your goal is to identify which gas is which. You need to follow this procedure to the letter, guys. You're going to be sending me lots of emails if you don't. So it gives you step-by-step instructions. Sometimes you have to press the shift key while you're clicking at the same time. This is very important that you do this X only with the axis. Look here, you have to use the shift key again. Do everything in order. Follow these instructions, and you will do just fine, okay? So let me show you a couple features here real quick. You'll have your spectrum. There's the lines, but you'll also see they're kind of hidden here because I've already gone over this step. There's a green dot and a red dot. These are for calibration. These are lasers. We know the wavelengths of this laser light. The green one is at 510 nanometers. Sorry, my units are off. It should be nanometers. And the red one is at 650 nanometers. That calibrates our spectrum. That helps tracker to know what is the wavelength of this red line, what's the wavelength of this blue line, because we have standards right there. So once you follow all those instructions, you will get a beautiful plot of the spectrum. Look here, those three lines, three peaks, and you will also get a nice table. Your job is to identify the wavelength of each.